Hello everyone, welcome to my calculus lecture. In this lecture, we study limits involving infinity and asymptotes. Okay, so why do we want to study limits involving infinity? So far, we have studied like limits involving only finite numbers, right? So now, we are, uh, the uh, getting into, the uncharted territory before, right? So limits involving infinity. Okay, so why this is important? Why do we want to study? Well, limits involving infinity has important applications. For example, it helps us sketch the graph of a function. All right, the this and also the techniques we are going to learn later on, like to where your function has a maximum or minimum, or so there's another like aspect of a graph called concavity. So where your graph is concave up, concave down, and so on and so forth. So these are all the important pieces for us to be able to sketch a graph of a function without an aid of computer, right? That's what the old time mathematicians were able to sketch pretty accurately the graph of a function without having any computer. I mean, computers didn't exist back then, right? Or like graphing calculators and whatnot. Another important application is it helps us analyze the long-term behavior of a certain phenomenon, not only in mathematics but also the in other like scientific areas, such as physics, biology, and economics, and so on and so forth. So the point is, the limits involving only not only like finite numbers but also involving infinity, are important. Okay, so here there are like with respect to the limits involving infinity, there are important notions about the asymptotes. Okay, so what are the asymptotes? Simply speaking, an asymptote is like a straight line where the graph approaches. Okay, so there are three important types of the asymptotes: horizontal asymptotes, vertical asymptotes, and something called oblique or slanted asymptote. Okay, so those three types are important types of asymptotes. First, a horizontal asymptote. So the line x equals a, as you can see, x equals a, that's what? A vertical line, right? Oh, yeah. I'm sorry. So actually, I'm supposed to talk about, vertical asymptote. So title is incorrect. Anyway, so, yeah, I want to talk about a vertical asymptote first. So the line x equals a, this is what? This is a vertical line, right? So the line x equals a is called a vertical asymptote of the graph of y equals f of x if the following conditions are met. So what are they? Limit of f of x when x approaches a from the right is going to be plus or minus infinity, or limit of f of x when x approaches a from the left, right? So the left hand limit of f of x at x equals a, in other words, is plus or minus infinity. When that happens, the x equals a is called, a vertical asymptote. Okay, a vertical asymptote. So what does this mean, right? What it means is that when x approaches a from the right or left, so right hand limit or left hand limit of f of x, right, at x equals a is going to be infinity or negative infinity. What that means is, you know, the graph of f of x gets closer and closer to, right, gets closer and closer to the vertical line x equals a, okay, as x approaches a, you know, from the right or from the left. So obviously, why this is called a vertical asymptote. Okay, so here's an example. Find the vertical asymptotes of the graph of the following rational function: y equals x squared minus 3x plus 2 over x cubed minus 4. In order to calculate that, let's go to my notepad. Okay, so here we have the function, right? So, we want to find the vertical asymptote of the function y equals x squared minus 3x plus 2 all over x cubed minus 4x. Okay, so when you have this type of like rational functions, right? Rational functions. So first, the candidates at which uh, the the vertical actually the candidates of uh, possible vertical asymptotes can be found by solving the equation x cubed minus 4x, the denominator, right, equals 0. Okay, so in other words, I said candidates. Okay, so the possible vertical asymptotes can be found, right, by solving this. So among those x values that make the denominator 0, right, we may be able to find the vertical asymptote. But what you have to be careful is may not be. So we find the solutions, right? But those x values that make the denominator 0 it may not be true that all of them are vertical asymptotes. Some may be vertical asymptotes, some may be not. So how do you find out? Well, we have to examine each one of them, each one of those candidates, okay, to satisfy the condition, right? Remember earlier, like we talked about the condition for a vertical line to be a vertical asymptotes, right? So you have to examine those. So let's first find those candidates, okay? Right here, x cubed minus 4x, that is factored to, so first, x is a common factor, right? So if you factor x out, we get x squared minus 4 remained, right? And x squared minus 4 is factored to x plus 2 minus x minus times x minus 2. So set it equal to 0. So we have three possible solutions, right? X equals, in this case, negative 2, 0, and 2. Okay? So they are just the candidates. Okay? These are just the candidates. We don't know at this moment whether like all of them are vertical asymptotes or some of them. Some of them, then which ones, right? Okay, that's what we have to figure it out. So first, when x equals negative 2 case, so let's determine whether this x equals negative 2, this vertical line is actually an asymptote, right? To see that, we will have to calculate, right? We will have to calculate the left-hand limit and right-hand limit at of the function, right? At the x equals to negative 2, right? So first the left-hand limit. Okay, so that's limit x approaches negative 2 from the left side, right? As you can see, right, so what happens here, the top part, right, and when x approaches 2, the top part is negative 2, right? So negative 2, so that's going to be negative 2 squared minus 3 times negative 2, okay, plus 2. So that's going to be 4 plus 6 plus 2, that's going to be 12, right? That's going to be 12 all over. Down here, that's 0. That's 0, okay? But in this case, it is not 0. It's infinitesimal. Remember that? It's not number 0. It is, although we call it 0, okay, conveniently, for convenience, but it is actually not the number 0, but an infinitesimal. Now also, another important thing about infinitesimal you would have to remember is what? Infinitesimal, not like number is neutral, right? So there is no sign. But in case of infinitesimal, it can be positive or negative, right? We talked about that. So in this case, top portion is the numerator is not 0, so that's 12. So actually it is important to know whether like it is positive infinitesimal or negative infinitesimal. So how do we see that? Well, remember, so this is important, okay, so x cubed, right, x cubed minus 4x, right, it is factored to x times x plus 2 times x minus 2. So this is something, you learned in, elementary algebra, okay? Right. So we can easily sketch a graph of this. I mean, not the exact one. We don't need the exact one, but, briefly, right? Let me, yeah, previously I didn't utilize this. So, it got kind of like ugly, but I can actually draw lines nicely. Okay, so these represent x-axis and y-axis. Okay, and so I'm going to plot those, the 3 points here, right? So x equals, let's say this is -2, 0, all right? This is 0, and also 2 here, right? And the leading coefficient is 1, which is positive. So in that case, the tail, if you remember what you learned from basic elementary algebra, right? So the tail goes up, right? So the only possible choice in this case is going to be this kind of curving. So let me use actually different color, right? So it goes like that. So that's gonna be a very very brief sketch of this function here. So anyway, but that's good enough to analyze it, right? What's going to happen? So what we have it, is this going to be like a positive infinity, infinitesimal, or negative infinitesimal, right? So here x is approaching -2 from the left side. So here, look at that. In that case, the graph is what? Below the x-axis. So you can easily see x is approaching -2 from the left case. The function approaches 0 while retaining negative sign. So it is actually negative infinitesimal. Okay? So for negative infinitesimal, I'm going to use this notation. Zero negative. Okay? So we have a 12 over 0 negative. Right, so a constant is the numerator is a fixed number. Constant, bottom part gets closer and closer to 0 while retaining the negative sign. So overall, what is this? This is a negative infinity. Okay, negative infinity. Anyway, so this does satisfy, right? This does satisfy the the condition. Okay, the condition for being a vertical asymptote. So we know that x equals -2 is a vertical asymptote. However, we also would like to calculate right-hand limit as well, okay? Because that piece of information is also important, for instance, to sketch a graph of this function here, okay? Right. So later on, I'm going to show you how these pieces can be put together to sketch a graph of a function. So x squared minus 3x plus 2 over x cubed minus 4x. So in this case, the numerator is still 12, same thing, but the denominator is going to be gonna go to 0, infinitesimal, but what is going to be the sign? From this graph here, that's obvious that when x approaches 2 from the right side, the right hand limit of denominator is going to be 0 positive infinitesimal. So that's gonna make the overall value positive infinity. Okay? Right. So anyway, x equals -2 is a vertical asymptote. All right, so next one we want to examine is x equals 0. Okay? Before we go on, so this is a vertical asymptote. Good. So far, so good. So x equals 0. To see that we do the same thing here, okay? We are going to do the same thing. So we first calculate the left-hand limit at x equals 0, right? So x squared minus 3x plus 2 all over x cubed minus 4x when x approaches 0 from the left. So top part, that's easy. 2 over now bottom part to see what's going to happen to the denominator, right? Let's take a look at the graph again. X is approaching to 0, right? X is approaching 0 from the left side. In this case, the graph is what? Above the x-axis. So, it's going to be 0 positive. So, positive infinitesimal. So that's going to be infinity. So we now know that x equals 0. This vertical line is going to be a vertical asymptote. Okay, but again, we also want to calculate limit of x squared minus 3x plus 2 over x cubed minus 4x when x approaches 0 from the right side. All right? Um, so that's going to be 2 over, when x approaches 0 from the right side case, the graph is below x-axis, so it's going to be 0 minus. So negative infinitesimal. Overall, so this whole thing is going to be negative infinity. Good. Now lastly, we are going to examine x equals 2. Okay, so limit x approaches, actually what happens is that this is not going to be. So actually it's not. Let me give you a heads up. This is not a vertical asymptote. How do we know? Because in this case, the limit does exist. X squared minus 3x plus 2 over x cubed minus 4x. The limit of this function when x approaches 2 does exist. How do we know that? Where, when x goes to 2, x approaches 2, that's 4 minus 6 right, 4 minus 6 plus 2. So that's 6 minus 6, 0. The bottom part is also 0. So this is a 0 over 0 type indeterminate form. Well, in this case, if you recall, we can evaluate this limit by factoring both the numerator and the denominator, right? So this equals limit x approaches 2. So the numerator is factored to, in this case, x minus 2 times x minus 1. The denominator we already know, right? X minus 2, x plus 2. Okay, so the numerator and the denominator have the same factor, x minus 2, so we can cancel it out. Why? Because x is approaching 2 means that x is never equals 2, right? again, by using like analogy of uh, a ridiculous arrow, which it gets closer and closer to the target, but it never hits the target. Okay, right? That's the thing. So x minus 2 is never equal to 2, while it is, getting very close to 0. Okay, but it is never equal to 0. So you can divide the numerator and denominator by the same number, x minus 2, right? So that's what the canceling is about. So this leaves us limit x minus 1 all over x times x plus 2 when x approaches 2. So in this case, that's going to be 1 over a. Okay, so a finite number. So limit does exist, and so in this case, x equals 2 is not a vertical asymptote. Okay, so two of them, x equals negative 2 and x equals 0, those are vertical asymptotes, and x equals 2 is not a vertical asymptote. Okay, so let's go back to my lecture slides. Okay. So next thing is really horizontal. So previously we were talking about vertical asymptotes. So this time we are going to talk about another type of asymptote called horizontal asymptote. So here comes the definition. A line y equals b. So obviously, that's a horizontal line. A line y equals b is called a horizontal asymptote of the graph of y equals f of x if the following conditions are met. So what are they? Limit of f of x when x goes to infinity equals b, or limit when x goes to negative infinity of f of x equals b. Okay, so what does this mean? What it means is that, you know, the when x gets larger and larger in either side, like, so when x goes to infinity or the other side, the negative infinity, the graph of f of x gets closer and closer to the horizontal line y equals b. So that's why it is called a horizontal asymptote. Okay. So here's an example. Find the horizontal asymptotes of the graph of y equals the same function we talked about earlier, okay? So x squared minus 3x plus 2 over x cubed minus 4. So to discuss this, let's get to our my notepad. Right, so here we want to find the horizontal asymptote of the function of the graph oh, graph of y equals x cubed no, sorry, x squared minus 3x plus 2 all over x cubed minus 4x. Okay, right. So in this case, we want to calculate limit x approaches, no, x goes to infinity, right? X squared minus 3x plus 2 all over x cubed minus 4x. All right? Okay. So how do you calculate something like this? Because when you do this, that's going to be infinity minus 3 times infinity, still infinity, right? So infinity plus 2. So you get like what, the infinity. So overall, like, you see like infinity minus infinity, right? Okay. And then suddenly, like, you might say, oh, you know what, this is equal to 0. You get the same thing down here also, right? Infinity minus infinity. Uh, but it is not. It is not 0. Why? Because infinity is not number. And also, we are writing down the same notation, right, for this infinity, infinity. But not every infinity is, are equal, you know, because some, blows up quicker, way quicker than, the other guy, okay? So although we are using the same notation for infinity, but, the state of infinity, state of blowing up to infinity is different. So the one may blow up quicker, a lot quicker than like the other guy. All right. So we don't know what's going on actually. Just by looking at this only. We need like some kind of further analysis. Okay, to see what really goes on. All right. So this is again another like what? This is indeterminate. Okay. This is in indeterminate form. Okay, just like 0 over 0. There are also, the other types as well. We're going to talk about them later on. But so how do we deal with this? When you have like infinity over infinity, infinity minus infinity type, indeterminate form, where actually there's an easy way to deal with this. All you have to do is to divide top and bottom, the numerator and the denominator, by x to the highest power. Okay, so the leading, leading term, right? The leading term. So in this case, the x cubed, right? So that's has like what, x to the highest power, right? That because that's leading term. So divide the numerator and denominator by this x cubed, x cubed. So if you do, what do we have? X squared divided by x cubed, that's going to be 1 over x, right? That becomes 1 over x minus 3 times x divided by x cubed. That's going to be 3 over x squared plus 2 divided by x cubed, right? Down here, x cubed divided by x cubed, that becomes 1 minus 4x over x cubed. That's 4 over x squared. And then now what? Here's one thing you've got to remember. Okay, you've got to remember. I mean, the Poland. So actually, I'm going to that's the important thing. So I'm going to put a box around it. Maybe I use red. Here's my box. limit of 1 over x to the power n when x goes to infinity, okay? Right? Or negative infinity. Here, n is a positive integer, okay? X is a positive integer, right? So, x equals 1, right? X equals, it could be 1, 2, 3, 4, and so on and so forth, right? In this case, that's going to be 0. The same thing can be said also limit, you know, 1 over x to the power n when, the x goes to negative infinity. Again, the n is a positive integer, right? So this is going to be 0 also, okay? So that's an important thing we need to know. So using that, what happens here? So, actually I don't need this limit anymore, but so using that limit, this guy goes to 0 when x goes to infinity, this guy goes to 0, this guy goes to 0, and also this guy goes to 0. So overall, what do we have? We have 0 over 1 equals 0. Aha. So actually, the x equals 0, sorry, y equals 0, the horizontal line y equals 0, which is x-axis, is going to be the a horizontal asymptote, right? A horizontal asymptote. And also, we want to calculate limit x goes to negative infinity, right? X squared minus 3x plus 2 all over x cubed minus 4x. We want to calculate this one also, right? But by doing the same calculation and using this limit here, right, we also found that this is going to be 0 as well. So in this case, actually, there is only one horizontal asymptote, right? So y equals 0. So this is the conclusion. Y equals 0. In other words, the x-axis is the horizontal asymptote. Okay, so there is only one horizontal asymptote. Okay, so let's go back to. All right. So by the way, before we continue, all right. So now we know the horizontal asymptote and vertical asymptotes, right? So how these two pieces of information can be used to sketch a graph of this rational function, right? This rational function. Of course, in order to sketch a graph of this function more accurately, we need more, the information, okay? But those things require the techniques that we are going to study in the later part of my calculus lecture, okay? Differential calculus uh, uh, lecture, later on about like, I mentioned earlier, but, you need like what, where maximum and minimum values uh, are located, right? I'm not talking about like in this case, there are different types of, maximum and minimum values, absolute maximum, absolute minimum, relative maximum, relative minimum values, and all those things, and also where the graph of the function is concave up or concave down, and so on and so forth, right? But we are going to talk about them later on, right? So, but using even like these two, like vertical asymptotes and horizontal asymptote, we can make a sketchy brief sketch of the graph here. Okay, so let me talk about that. So I'm gonna need the axis, right? So I'm gonna draw a line here. Okay, so yeah, I have never used a draw coordinate system. I don't know how that. Uh, no, no, that's not what I. Okay, so these are the uh, coordinate axes. So x-axis, y-axis. Okay, and now I'm gonna draw the what's that? The two vertical lines. Okay, so I am going to actually use it different uh, right uh, uh, color, right? So that's actually x equals uh, -2, right? And x equals 0. X equals 0, by the way. So so that's -2. Okay, x equals -2. This is 0, and and also the x-axis, that's horizontal line, right? Horizontal, uh, the asymptote, right? And we have two vertical asymptotes. Okay, and if you remember, when x approaches, right? So let's go back. It was actually done in the previous page. So when x is negative, x approaches -2 from the left side, that's negative infinity, right? That's a negative infinity. Right-hand limit at x equals -2 is a positive infinity, right? X equals 0 case, left-hand limit is infinity, right-hand limit is negative infinity. So using these two together, okay, and also the x-axis is when x goes to negative infinity, y goes to 0. So as x gets larger and larger in the negative direction, the graph gets closer to the x-axis, and then when x approaches -2, x approaches -2, from the left side, it becomes what? Negative infinity. So the graph goes like this. Okay, briefly speaking, yeah, it's gonna. Oh no, that's terrible. Okay, so it's gonna go like that. Okay, so gets closer to the vertical line, -2. And then when x approaches -2, so right-hand limit at x equals -2 goes to infinity, right? Remember? Okay. And then the left-hand limit of the graph S0 is a positive infinity. So it's a continuous function, and so what that means is like your graph looks like this kind of thing. Okay, so it goes like that. Okay, sorry, right? It's kind of terrible. Oh no, it's actually I'm making it worse. Hmm. Right, so it gets closer and closer to this, uh, vertical line. So that's the shape. And when x goes to infinity, oh yeah, and then also right-hand limit, right? Right-hand limit of the function at x equals 0 is going to be negative infinity, and then when x, goes to infinity, the what is that? The graph approaches the x-axis, right? Because that's a horizontal line. So, you're going to have this kind of shape here also in this case, something like that. Actually, it never touches, right? So that's incorrect. Oops, the yeah, it gets closer and closer to the x-axis. So that's a brief, a very actually brief sketch of the our rational function. Okay, so those pieces of information can be used to at least to briefly sketch the graph of a function. All right, so let's get back to my the lecture slides. So last type. So here comes the last type of asymptote. So it's oblique and slanted asymptote. Okay, so it's a oblique or slanted asymptote. So either is fine. An oblique or slanted asymptote can be seen from a rational function. So, it appears when you have a rational function, but not every rational function does have an oblique asymptote. But when the degree of p of x, so what do we mean by degree? Degree is what? The power, right? The power of leading term. That's called your degree. So the degree of p of x is greater than degree of q of x. So that's when we observe an oblique or slanted asymptote. An oblique asymptote is given by a dominating term of such a rational function. So what we mean by dominant term. Dominant term. So dominant term is like when x gets larger and larger, right? So one part of you know the rational function gets smaller and smaller, and the that leaves like the a dominating term. Okay, right. So you're gonna see that actually from this example here. So let us take a look at a simple example. Okay, right. So find the oblique asymptote of f of x equals 2x squared minus 3 all over 7x plus 4. So, that's a simple rational function, right? To see that, let's get back to my notepad. I don't have much space left, so I guess, I'm gonna move to a new page. Okay, so we have, right, so find the oblique asymptote of f of x equals 2x squared minus 3 all over 7x, right? It's a 7x. 7x plus 4. Okay, so how do we do this? Well, first step is we actually divide. We divide. Okay. Maybe I'll give you like the quick heads up. So what we are actually trying to do is same as the following. So if you divide, right? So if you divide, say 7, okay, 7 divided by 2, okay. So if you divide it 7 by 2, right? What happens? So I want to do actually long division. It's not going to be really long, but it's a so 2 times 3 equals 6. So what's remained is 1, right? So in that case, like when you divide the 7 by 2, that's the quotient, right? That's the quotient equals 3, and then remainder equals 1. So in this case, 2 over 7. So 7 is what? 2 times 3 plus 1, right? Okay, divider times quotient plus remainder. Okay, so 7 over 2, if you divide this guy by 2, 7 over 2 equals, the 3 plus, that's the quotient, right? Plus 1 over 2. Okay, so we can write it this way. Okay, so that's exactly what I'm going to do. So to do that, we will actually have to divide, right? 2x squared minus 3, right, by 7x plus 4 using a long division, right, by doing a long division. So here notice that, I intentionally left a space between these two. The reason is that there is no x term, right? There is no x term, means the coefficient is 0. So I made actually the room, right, the space for x term there also. Okay, so first we want to get rid of the 2x squared, right? To do so, you will have to multiply 7x plus 4 by what? 2 over 7 times x, right? 2 over 7 times x. So 7x times 2 over 7 times x, right? So that remains what? 2x squared. And then 4 times 2 over 7, x is going to be plus 8 over 7x. Now we are going to subtract it, right? We are going to subtract it. So if you subtract it, so these two will be gone, and that leaves what? That's negative 8 over 7 x, negative 3 comes down as it is. Okay? So now next step is we're going to get rid of this, right? Negative 8 over 7 times x. To do so, you will have to multiply 7x plus 4 by what? Negative 8 over 49. Negative 8 over 49. So if you multiply 7x by negative 8 over 49, that leaves negative 8 over 7x. And then 4 times negative 8 over 49, that's going to become 32. Negative 32 over 49. Okay, and then we are going to subtract it. Okay, so subtract these two will be gone, right? And so negative 3, and since we are subtracting negative 32 over 49, that's going to be positive. So that leaves 32 over 49 minus 3, that equals negative the 49 times 3 is going to be 147. So that's going to be negative. So 32 minus 147, that's going to be negative 115 over 49. So this is the remainder. Okay, this is the remainder. So just like a number, in this case, so what is that? 2x squared, right? 2x squared minus 3 equals, right? Divided 7x plus 4 times the quotient. What was that? That was 2 over 7, right? So 2 over 7 x minus 8 over 49, 8 over 49, plus the remainder. So the remainder is in this case negative 115 over 49. Okay, so if you divide this by 7x plus 4, that leaves 2 over 7x minus 8 over 49 minus 115 over 49 times 7x plus 4. Okay, so how does this help to find an oblique, the oblique asymptote? So here's what happens. Okay, we are talking about for large x, right? So for large x, so when x goes to you know here, this term actually goes to 0 as x goes to infinity or x goes to negative infinity. Okay, so when x becomes larger and larger in the positive direction or negative direction, this term gets smaller and smaller, so it goes to 0. So what's going to happen here is that, in that case, this is going to be the leading term. Okay, that's the leading term. So for large x, in the positive direction or negative direction, what matters most is this term, not the other guy. Okay, so this is going to be the leading term. Okay, so that's it, the leading term. So that's actually the oblique, right? This is the oblique asymptote or slanted asymptote, whichever you want to use. Okay. All right, so going back to my lecture slides. Yeah? No, I'm sorry. That's not the leading term, but dominating term, right? Okay, right. Maybe I wanna change it, the terminology. So not the leading, yeah, but the correct word is the dominating. The dominating term. So that's the oblique asymptote. Okay, so this is it. Uh, the more details of my discussion in this lecture can be found in my lecture note at the following address. So as usual, I made a hyperlink there. So, by clicking on this address, uh, uh, you will get to my lecture note about, the discussion we had here, all right, in this lecture. And also, if you want to visit my main Blogger site, just click on this word Blogger, which is also hyperlinked. Okay, so thank you for listening and watching, and I'll see you next time. Thank you. Bye bye.